Personally, I'm a big fan of testing. Seeing tests fail after I make the change feels great. It's like a friend in the past warning me against making a mistake. When I practice test-driven development, I almost always end up really liking the code that I write. As a package developer, having a passing test suite makes me feel confident that the work that I'm asking other developers to rely on actually does what I told them that it does. Plus, showing a CI badge on my libraries makes me feel like my work looks polished and ready for the world. But even though I'm a big fan of testing, sometimes I find myself really hesitating to actually write them. And often, I find myself hesitating to write tests exactly when they seemingly be most useful, when there's a lot of complexity. When I've got a complex application, when the state isn't trivial and there's a lot of data to work with, and too many conditions to list, it's really easy to talk myself out of adding any tests. Things are complicated and confusing, and I'm afraid I'm going to make a mistake. I feel like I don't understand how the application works, and I don't know what to expect. It's hard to test, so I don't. And then the next time I touch the code, things are worse. How can I write expectations when I don't know what to expect? When my assumption is that whatever the application does must be correct? When my knowledge about what the application should do is limited to my intuition and to what the application appears to do? My pitch is that changing how your code is written can make testing easier. Essentially, my answer to the question, how can I write expectations when I don't know what to expect, is rewrite the code so that you always know what you expect. All right, so I've prepped some example code, like a little mini example application, and we're going to play with it to explore this idea. How to change code to make it more testable. So we've got some new to us application code, and we've also got a bug report. The bug report says, on the logged in dashboard, the ticker showing the time that the user has been active shows negative values. We find our application code and look at the folder's contents. There's flags, init, main, model, port, update, view files in the source folder, and then there's a test folder with an integration file. Okay, so we can more or less guess where the different pieces of the application live. Plus, it looks like there are already some tests. Let's take a look at that test and see what we have. First, the imports. We're importing a great deal. Flags, init, model, and view are all necessary to set up the application. Then we need to be able to make assertions, so we need expect. And we can assume we're using test.html query and test.html selector to test the rendered HTML. Reading down a bit more in the file, we find a single integration style test that claims to check that the page renders. First, we try to decode our JSON string. Maybe this fails. If so, then the test fails. If not, then we initialize the model and discard any initial commands that the init function produces. We pass the model to the view function. Then we convert our view to a format that we can use elm-test to test against. Finally, we run our actual expectations against what copy shows on the page on load. So what is this test really testing? Well, we'll know if our decoder fails to decode the JSON string that we use in our tests. And we also know what the initial state of the view will be. But mostly, this test checks copy. This test is helpful for us to look at to get a sense of what the application does, though. Apparently, initially it shows a welcome message and placeholder times. With a brief skim of a simple test, we have a solid sense of what the program is about. It's pretty powerful to be able to look at one place in an unfamiliar code base and know at least a little bit of what's supposed to happen. So even though this test doesn't actually do much to protect us against accidentally breaking behavior, it does give us value as a note, one that can't get stale to future collaborators. Some engineers, when reading code, read type annotations first. Other folks find themselves drawn to comments. Some folks prefer to start inferring meaning from just function names and variable names. And some people start out on a project by reading tests. As engineers on large code bases, our interaction with code can't feasibly be strictly linear. We can't read through all the code that we use and all the code that we rely on. We're only ever looking at a piece of a much, much larger puzzle. And the pieces that I choose to pick up and examine might be different than the pieces that you reach for. Which is to say, even if you personally don't find much value in reading through an integration test, like the one I just showed, your collaborators might feel differently. Tests have collaborative and historical value beyond stopping the occasional bug. At any rate, we know that our integration test doesn't yet test that the view includes the text, "You've been active on this site for 1 second." Searching for the phrase, "You've been active on this site" in the codebase, we land in the view file. In a let block, it looks like we're defining a seconds active variable. To find this value, it looks like we're using a function from the model module that returns a maybe integer. We're defaulting to some underscores in the view if the user hasn't been active, and then we're using this string in the view. This code means that there's a function called seconds active somewhere that we should be able to write some unit tests against. Looking at that function, seconds active takes an entire model, whatever that is, and returns a maybe in. In the function body, we're using 2 fields, something called active sense and something called current time. Both fields are maybes. What information does this give us? What does this tell us? For one thing, to test this function as it is, we'll need a fake model fixture of some kind. We also know that for tests to be comprehensive, we need to consider 4 basic combinations of active sense and current time values. In case where active sense is nothing, current time is nothing, active sense is a value, current time is nothing, active sense is a nothing, current time is nothing, and active sense is a value, and current time is a value. Scrolling up in the model file, we can see the necessary shape of the model. Let's add a model spec file matching the existing folder structure, and then let's write a test. So to start with, our imports are pretty straightforward. We need to be able to write tests and make assertions, so we import expect and test. We're testing a function from the model file, so of course we need to import it. And then the function that we're testing is dealing with time, so we'll need time too. And then we have our 4 cases. Active sense is nothing and current time is nothing. Active sense is a value and current time is nothing. Active sense is a nothing and current time is a value. And active sense is a value and current time is a value. Great, easy. So writing out our expectations for the first case, where active sense is nothing and current time is nothing, things aren't so bad. When we don't have either a current time or an active sense value, seconds active ought to return nothing. Seems reasonable. And then if we want to, we can make a test fixture. We can pull out like a dummy model helper that sets up a fake model and then use that in our tests. So that's fine. Things are going great. Let's move on to the next case, where active sense is a value and current time is nothing. All right. Oof, like that's confusing. Now we've got to have this dummy user variable so that we can have a model with a user with an active sense maybe value that we can control. And then we still have this other case where active sense is a nothing and current time is a value, which should also return a nothing. And finally, we have the case that theoretically we actually care about, where we have both an active sense value and a current time value. So in our test setup, we set up both an active sense value and a current time on the model, and then use seconds active, and essentially double check that we're doing subtraction right. Okay, so let's run these, now that we have some tests. These pass. All of them pass. We were trying to write a regression test. The last test was supposed to fail. Was the bug misdescribed, or did we just mess up somewhere? Well, we messed up. But the way that the setup works for this test, it's not immediately apparent how we messed up. We set both the active sense time and the current time to the same value, and the difference between these times is 0. Since we just wrote this test and need to commit a regression test, we can just change our setup values to be more useful. If we weren't the authors of this test, though, and weren't familiar with the code that it's testing, this test would be intimidating to change. The fixtures and the setup look complicated and easy to mess up. Imagine a more complex application that you're seeing for the first time. Tests in this style will be hard to understand. Active sense is a value and current time is a value. What on earth does that mean? And which of the many, many values on the model actually matter to the calculation? In writing these tests, we had good intentions. We were trying to leave the code base better tested than we found it, and we were trying to be good code base citizens. But the next person to look at these tests is going to be afraid to remove them. It's going to hesitate to refactor the model for more simplicity, and is going to believe that the seconds active function is more complex than it actually is. So how did this happen? How did we go from having a quite simple application to having a test suite that makes our code, by some measures, harder to maintain rather than easier to maintain? Our testing difficulties stem at least in part from how we've structured our code. Currently, we're exposing 5 types or type aliases: flags, user model, user again, and message, and we're exposing 6 functions that we could reasonably test: decoder, init, seconds active, update, and view. But none of these functions really make any sense independently of each other. This is obviously the case for the components of the Elm architecture. For example, the view requires the model, and the result of the view is tied by the type system to the message type, which is used in update. But this is also true for seconds active. Seconds active also only makes sense in the context of the other modules, since seconds active operates exclusively on a structure that only makes sense in the context of these other modules. None of these modules can stand on their own. None of these modules make sense on their own. It's no wonder that our tests make seconds active look complicated, when seconds active kind of is complicated. It's part of this tangle of functions and types. So let's try restructuring and move all of our various pieces into a single main module. Once we make this change, we find that our imports are simplified to just browser, HTML, JSON decode pipeline, task, and time. In restructuring, we run into 2 type aliases called user. One was previously defined in the model file, and one was previously defined in the flags file. Having this kind of repetition in naming suggests that we might have a self-contained idea of a user in this code base. We can fix the naming collision with a simple rename, but we can also pull user out into its own module. If we pull user out into its own module, we won't have to worry about naming collisions as much in our main file, and the code might be a little easier to keep in our heads. Plus, if we wanted to test our initialization logic or decoder logic for a particular user, it'll be a bit more straightforward. Okay, so our updated file structure looks like this. We have a main file, a user file, and an integration test file. Restructuring immediately improves the ease of setting up the integration test. We no longer need a literal bajillion things to set up our test. We're not done with our code changes yet, though. Currently, seconds active depends on the entire model. This dependence needlessly complicates test setup. Not only that, but depending on the entire model, it makes it practically impossible to actually guarantee that the function works as desired through tests. Why? Let's think about this from a types first perspective. How many possible implementations are there for a function with a type annotation saying it can take any type and will return that same type? No matter the name, this is the identity function, and there's only one possible implementation. For a function to accept some generic A and return the same type A, that function can only do one thing: return its argument. Consider, on the other hand, a function that takes a string and returns a string. What might happen in the function body? There are an uncountable number of possible implementations. Anything might happen in the function body. The less specific the type of a function, the fewer things the function could possibly do. The more things a function could possibly do given the type system, the more valuable your unit tests will be. Which is to say, the type system can't prevent implementation errors, but you can through tests. If you want a truly excellent function that takes a string and repeats the string 3 times with dancer emojis in the middle, then it makes sense to make sure that the function you write actually does that. For our code, when we have seconds active take the entire model, not only are we making test setup way harder than it needs to be, but we're undermining the type system's ability to help us. Thinking only in terms of the type annotation, it's possible that the maybe int that seconds active returns depends on any fields in the model that we pass in. The type system can't read our intention that seconds active depend on sensible fields only. From a types perspective, there's nothing preventing the body of this function from using every field the model contains. Those unit tests we wrote against the active sense function, those still pass even when we change the implementation to depend on the user's first name. For full and complete tests against seconds active, we'd need to have tests against all possible different values in the model. A model which has a user field with 2 string fields, 1 maybe strings, 1 POSIX time, and 1 maybe POSIX time, in addition to having a current time field. The possible number of combinations of these fields is vast. which means that as long as the seconds active function depends on the entire model, the seconds active function isn't really constrained by the type system. We can't really consider it fully tested. Even in a type-safe pure functional language like Elm, getting to full coverage of a seemingly simple function like this one is practically impossible. So how do we test this? The best way to test it is going to be to change the code that we're testing so that it's easy to test. When we use a type alias to mandate that data be passed along, we're really writing a shorthand for the code on the right. We'll end up with different compiler errors with and without the type annotations, but in terms of complexity, we're talking about more or less the same thing. So let's see if we can't get rid of some of this extraneous structure, starting with the outermost layer. Let's remove the maybe wrapping the current time. Since a function that calculates how long a user has been active doesn't really need to care whether we know the current time yet or not. Displaying nice default values to the user when we don't have enough data yet is a view concern. It doesn't actually matter to the calculation that we're doing. By changing the type of seconds active to accept a current time in a user, we've eliminated one layer of structure, but there's still a lot of variability in the data that user contains, as is apparent in the expanded type annotation in the right-hand version of this code. If we fully unwrap the data we need from user before the seconds active function, we end up with a much simpler function, a function that will be easier to test. However, it may be harder to use. Developers who want to use this function will need to dig around to figure out argument order. I think that this trade-off may be one of the reasons that folks often pass around large records. Having functions that take type alias records means you can't mess up argument order. But that's not a trade-off that we need to make. We can have both an easy-to-use API and easy-to-test code. The smallest change from our existing API is to describe an extensible record with at least the data that we care about. Or maybe we could pass both fully unwrapped arguments through in a single record. Or maybe we define custom types, current time, and active sense, and use them so that the type system enforces that arguments are passed through in the right order. Fundamentally, the idea that I want to emphasize is that the less extraneous data your functions pass around, and the more constrained by the type system, the happier you'll be with your tests. Once our failing function relies only on the data it needs, and once we've got confidence that its arguments are what we think they are, we can write a test. And when we run the test, we find that it's a real regression test, one that actually fails, and passes once we fix the bug. We had been subtracting the current time from the active sense time, flipping the direction of the subtraction fixes the issue. We might also notice, now that some of the surrounding complexity is gone, that if a user hasn't got an active sense time, that means that they've been active for 0 seconds. Eliminating unnecessary structure and return values is pretty great too. We should, of course, add a test against the second branch here. In general, reducing extraneous structure around the values that matter, including both arguments and return values, makes understanding our code easier. And understanding what code is intended to do is a prerequisite for writing valuable tests. All right, so when seconds active depended on the entire model, moments ago, a lifetime ago, I claimed that it was impossible to get to full test coverage because the possible arguments to seconds active were uncountable. Even now, though, our seconds active function depends on 2 POSIX values, which are not exactly conveniently enumerable. So can we actually say that we have full test coverage? Well, you could quibble over the definition of complete code coverage, but what we can agree on is that our existing test only verifies that we get the result we want for a single pair of arguments. For this example code, that's probably sufficient. But for more complex code, being able to describe the properties that you expect your code to uphold, and then to have your code's adherence to those properties spot-checked is really powerful. And this is where fuzz testing comes in. With fuzz tests, we can write assertions against our functions using randomly generated but type-appropriate structures. If we define a property, seconds active is always greater than or equal to 0, for example, we can test that property. In my experience, fuzz testing is a great idea when performing complex string operations and numerical calculations. Even when fuzz tests don't find bugs, they've helped me to write better code by forcing me to think critically about what properties actually matter in the system I'm working with. Having a firm handle on the mandatory properties in the system can illuminate what what things in the system can be changed. Okay, so we've done a lot of things. We've restructured our application. We've written unit tests. We've thought about and tested the properties that we care about in our system. But do all of our pieces work when they come together? So we've got a head start on this since we've got an existing integration test. It requires a tedious amount of setup and only tests the fallback values in our application. And we're not really testing against the values that we expect our users to actually see most of the time. So let's deal with the tedium part first. So Novating engineer Aaron Bonderhar created and maintains a package called elm-conf, which is aimed at making testing applications more convenient. If you're interested in having fast integration tests written in Elm, seriously consider using elm-conf. The first step in using elm-conf is to set up a testing context for your application. If you're following the Elm architecture, this step will look very familiar. For an element, the pieces you need are just your initializing function, your update function, and your view. Depending on how your starting data is entering your program, if at all, you may need to pass a decoder and some flags through to fully set up your testing context. Then once we have a program test, we can conveniently test user-facing parts of our application as we simulate user interactions with the view without needing to manually manage the changes that our update function makes to our model. We can easily simulate effects and button clicks. Okay, so using our program test context, we can rewrite the integration test we had before. This code looks about the same as it did before, but now we can easily tick time forward. And then without needing to manually deal with our update function or model, we can make assertions about what the new view should show. And we can keep ticking time forward and making assertions about how the view should behave as many times as we want. We might even find a grammar-related bug to fix. Now, there's a piece of this integration test that I've been ignoring. JSON. Where did this JSON value come from? The edge of our application where JSON comes in is dangerous. That's one of the places where our application is likely to fail, and where it's likely to fail without recovery. Failures at the decoder level might mean that our users get no experience at all, rather than just a subpar experience. So it's important that we, at a minimum, spot check that our JSON will be decodable. So how do we make sure that our decoders work, given that managing lots of JSON strings by hand would be a pain? At Nerd Inc., we've used a couple of different approaches. In many of our newer features, we don't actually write decoders at all. We generate them directly from a Haskell backend. This is neat, but since having auto-generated decoders essentially means that you've eliminated the need for testing your decoders, I'm just gonna move right on by this. The vast majority of our code base is backed not by Haskell, but by Rails. We don't have guaranteed types when we get to the front end. These days, we generate test JSON using a tool built by Nerd Inc. engineer Josh Levin called Rails Edge Test. We use this test JSON in our Elm integration tests, in addition to verifying that the test JSON matches the JSON schema. We can feel fairly confident that our JSON decoders work. At the very least, they work for the happy path. And we don't have to manually muck with JSON strings whenever our endpoints or APIs change. This approach is often useful when you want to write tests against behavior that's behind a feature flag, say. Whatever strategies work for your backend, I highly recommend verifying that the data that you expect to hit your decoders is what actually ends up there. Your decoders will do exactly what you ask them to do. And it's worth the time and effort to make sure that what you ask them to do is going to work. Okay, so I threw a lot of opinions and code at you, but there are really just a few ideas that I hope you'll carry away from this talk. Key ideas. Okay. So first, test the breakable bits. Be sure to test both the edges of your program and your logic. If there's one thing that I never get wrong, it's not Booleans. And I won't stand up here and say that I would bet against your brain being different. 2, test for people. Tests can serve as developer tooling and as a collaborator tool. Tests can drive the design process and illuminate the core properties of the system in your own mind. Also, social applications can be great for motivating behavior that you kind of wish you would do for your own sake, but know that you won't. So if you won't write tests for yourself, try writing them for other people. And 3, lean on the compiler. People often say that refactoring in Elm is cheap. If you believe this, but also believe that testing Elm code is hard, try refactoring your code with test writing in mind and see where it takes you. If, on the other hand, you think that testing Elm code isn't worth doing because the type system will prevent many mistakes, I encourage you to try doing the evil pair exercise in Elm and see what you discover. Even if trying out evil pairing doesn't change your mind, you'll have some fun. Thank you so much for hanging out with me this morning. I really appreciate your starting elm-conf on testing with me. I lurk on Twitter as T_Kelly9, and I'm on GitHub as Tesk9. Say hi on the internet or here. Thank you.